Hello, today we'll discuss our final project on using machine learning to classify bird sounds globally. I'm Elian Zacher.
I am Oleg Pavlov.
Hi, I'm Shane Kissinger. We're going to be talking about the model evolution.
Birds play a crucial role in our ecosystem. From pollination to pest control, humans need birds. Monitoring them is challenging, but it's crucial for their conservation, and that's where our project comes in. Our project focuses on using their sounds and their sounds alone for accurate classification, without the need of using geotags or other metadata information. Our machine learning model not only identified the species based on their vocalization alone, but handles a massive dataset of bird sounds from diverse regions, requires significant computational resources to standardize and analyze effectively these sound bites. Our data source is from the Zeno Canto Foundation, a comprehensive repository of bird vocalization recorded worldwide. The dataset includes over 700,000 recordings of more than 10,000 species, complete with detailed metadata essential for our analysis. To prepare our dataset for analysis, we've implemented noise reduction, sample rate normalization, and spectrogram generalization to standardize audio inputs. Our EDA shows the dataset's imbalances and varying recording lengths, guiding our pre-processing and modeling approach.
So we first started out training on a downsampled version of the spectrogram data that was provided in the original data set. And we downsampled it so much that we lost a lot of the information, which caused very bad accuracy, training accuracy and validation accuracy. And we also learned that it was because of this class imbalance that is inherent in the data set. And so for the next time, or for the next section of that, we downloaded a lot of the original spectrogram data for the 10 most common species in the data set, trained another model on that, and we got roughly 70% validation accuracy. And we noticed about that the classes were very deeply imbalanced, with the least being about 989 and the most being about 2000. For the third approach, we did transfer learning and a self-based audio-based model. And for those, I ask you to take a look at the notebook. We have that in there. For training and evaluating the model, we first started out by processing the MP3s. So we downloaded MP3 data for the 5 most common species, zeroed out the sections that were under 25 decibels, split those, and then looped them. That gave us a lot more training samples, solving the class imbalance issue. And then we also normalized and stuff like that. And so finally, then we took those MP3s and we created our own spectrograms, which we then fed into the model. These images were augmented with horizontal scaling and Gaussian noise. We fine-tuned the parameters, and we also calculated a bunch of evaluation metrics. And then so for the results, we saw that it did actually perform significantly better than the original starting model.
We thought to ourselves, could we do better? Could we improve on the performance? We decided to try a transfer learning pipeline and then to compare the results. For the pre-processing, we still utilized the silence threshold splits. We also had to transform the data frame into PyTorch dataset with the actual audio loaded. And we also used class-adjusted sample weights. So if there is any sample imbalance in the future, it is handled in the pipeline. For the hyperparameters, we selected 12 epochs, and for batch size, for example, which managed the computational resource of the kernel with the speed and performance of our model. For the results, we trained on 3,000 10-second samples per class, and we achieved 85% accuracy and around that F1 score. However, we had 94 million training parameters, and the model took 6 hours to run. And that is a lot of penguins. Overall, we are happy with our performance, 85% for 10 bird species. The bird species are wide range from the world. There is broad coverage, so we know our model works in different geographical species. And as we increase the sample size, we can also scale the performance. This can be used in ecological monitoring, scientific research, but also educational outreach. This is especially important considering the most recent discovery of whale language.
So we started with training on all images, then continued on training just on the sound, then cleaned up the sound and trained on that, and then ultimately we also used transfer learning. However, our final model is the one we trained on the audio, due to the fact that the transfer learning model took too much to process.
For the next steps, we would try to utilize a better machine to increase the sample size and maybe include the geotags in the future. However, for this model, we wanted to focus specifically on pure audio training. Thank you so much. I hope you enjoyed our presentation.